Thank you very much, first of all, for the invitation, for the opportunity to be part of this beautiful event. It's a great pleasure. I'm going to speak about the dimer model, as most of other people in the other speakers. And thankfully, the definitions appeared already a lot of times, so I don't need to spend a lot of time on this, but I still would like to introduce some of them briefly. So by dimer model, I understand a probability space associated with any finite bipartite graph weighted. Points in this probability space are dimer covers, and then probability of a given or perfect matchings of this graph and probability of a given dimer cover is proportional to the product of corresponding edge weights. Okay, so then the graph is planar, then something special is happening, and dimer model can be treated as a model of a random height. So the height can be defined, for example, as follows. We choose some reference dimer configuration D0, and then given a random dimer configuration D, which is blue on the slide, we superimpose it, we draw it all together with D0, and we get a collection of loops and double edges. Then any loop can be oriented in such a way that, say, all dimers in the reference cover are oriented from white to black. And then we think of the height function as of the function which has these loops as level lines. So it's not actually like level lines, but it's actually the only lines where it changes its value. So it's a function on faces which is constant between loops and jumps to plus or minus 1 when we cross a loop. And well, then we can take our graph, we can fix some face of it, declare it to be 0 in this face, so for example, the outer face if it's drawn on the plane, and this determines the height function everywhere. But this construction obviously depends on the reference cover. So if we change the reference cover, then we add something to our height function, some deterministic function which depends only on these two reference covers. So to get rid of the dependence, we can subtract the expectation. And then obviously the resulting object will not depend on D0. We call it height fluctuations, and this is the main object that we want to study in this talk. Okay. So questions so far? Okay. Yeah, this talk will be a little bit different from most of other talks in this workshop. So it will concern some some probabilistic property which appear in the scaling limit. So not too much discrete combinatorics, but some asymptotic of this object instead. So the general setup that we want to study can be described as follows. So we have a certain planar thing, like a surface, Riemann surface, or planar domain. So for a moment, let us think that it's a simply connected planar domain. And we have a sequence of graphs approximating this planar domain in a certain sense. So it's labeled usually by a certain parameter delta, which I call scale. And I think that this scale tends to 0. So for example, if we can think of an approximation by some lattice graphs, some subgraphs of regular lattice, and then this delta would be the step size of this lattice. So there might be some other different scales. And the general thing that we expect is that if this which heuristics tell us is that if this sequence of graphs approximate the sigma nice enough, and also if there is some constraints along the boundary satisfied, then these height fluctuations that we defined should converge to the Gaussian field in this domain, right? Yeah, so there is a non-trivial story happening with how this graph, the combinatorics of this graph along the boundary, but if it is nice, then it should convert to, it should have Gaussian fluctuations. Okay, and well, it's a big story about this. So there are many partial results, there are big open conjectures, but there is one thing that is very well understood in the case of simply connected domains up to the date. It's the case of Temperlian graphs. It's the case when these graphs are Temperlian. And yeah, so first of all, due to Rick works, but also to the work of Nathaniel, Ray, and Laslier, which some of them are in this room. Okay, So, but today we want to think about a little bit different setup. We don't want to treat a simply connected case, but we want to see what's happening when sigma is a Riemann surface. So it has non-trivial topology. So now, what is the actual setup that we want to study? We take a Riemann surface. Well, it might have a non-zero genus G. It might have some boundary, right? Some boundary components. So it's of finite type, but otherwise its topology might be as non-trivial as you wish. And we consider a graph, bipartite graph, that is embedded into our surface properly. Then we still can define the height function. So we fix a reference dimer cover, and we superimpose it with any other dimer cover, and we can try to start from some phase and compute the values of our height. And locally, it will be consistent, right? So because it's defined by local rules, no problem. Locally, it's like on the plane. But obviously, if we go around some non-trivial loop in our surface, we might catch up a monodromy, right? So for example, here, if you can see the previous example, but drawn on the torus, right? So then if you go in a parallel direction, we pick up in monodromy -1, right? That's the slide. So, well, we managed to define the height function, but it's now a multivalued function. From the definition, from local consistency, it's clear that the monodromy will give us some cohomology class. So it's like function on homology classes of loops with integer values, right? Yeah, and also it should be mentioned that if you had a boundary, then for the same reason, the height difference between boundary components would also be non-trivial. Okay, so it will also be a random thing. So now, yeah, we want to study globally multivalued functions with additive monodromy of this kind. Okay. So yeah, so here what we have, as in the previous, in the simply connected case, we want to subtract the expectation. So yeah, so it's our function will remain multivalued after we do it, but the monodromy will not be integer anymore. So it will be some integer shifted by some deterministic real-valued cohomology class. Okay, so now how we want to treat these objects? It's not a very well-defined thing, multivalued functions, so it's better to find some other more rigorous approach to the thing. So in this case, the most natural thing is to take the derivative. So remember that I said that our surface is a Riemann surface. It has smooth structure. So we can treat our function as a locally constant function on faces. Okay, so then we can take the derivative. It will be one form, which is, it's not one form with like functional coefficients, but with coefficients which are distributions. But okay, we can work with such an object. It will be closed. So then we can, since it's closed one form, we can apply the Hodge decomposition to it. And to decompose it as an exact form of derivative of some function plus some harmonic differential. So I guess that not all of you, so let me try to remember a little bit what is Hodge decomposition, just in case. So yeah, assume that our sigma is a tori, right? So for example, like this. And we have some closed one form. So yeah, so what can we do is we can find a linear one form that has same periods as these two, as this one form along two basic cycles. So we can decompose it in the following way. So we determine this linear one form, and then if you subtract this omega, this closed one form, and this linear one form, then the difference will have 0 periods. So we can integrate it and get a function. This means that we get the decomposition of this form. So one form is equal to some linear one form plus derivative of some function. And on a general Riemann surface, same thing can be done, but this linear one form is replaced with the notion of a harmonic one form. So it's again certain globally defined thing. Okay, so globally determined by the periods of the height function. So in this way, we get the following decomposition. So our function phi, which we call a scalar component, it kind of takes the responsibility of local fluctuations of h, how it behaves locally. And the component psi, you can think of it as a vector of monodromies of h, actually. So it's something that takes care of the global behavior of h. Okay? And as I said in the very beginning, we expect that height function has Gaussian fluctuations, right? So in the case of a simply connected, this tells us that in the limit, this should be the Gaussian free field. So what should be happening in the case of a multiply connected case? In the case of multiply connected sigma, then, the appropriate object in this case is what physicists call compactified free fields. So mathematically, one can think of it as follows. One can also think of it as of a sum, as a random one form that has two components: this scalar component d phi and instanton component psi. And this scalar component is simply Gaussian free field on our surface. Okay. And then the instanton component is random harmonic differential. And which constraints do we have on this? So first of all, we know that it is integer shifted by something deterministic, right? So it is kind of a discrete object. It has discrete distribution in the sense that it takes only countably many values. But still, so we have to define its distribution is enough to specify countably many probabilities. And these probabilities must be Gaussian. So the probability that this harmonic differential is equal to some particular harmonic differential specifying this integer valued constraint is proportional to certain exponent minus certain quadratic form, which is actually Dirichlet energy on the surface. Okay.
This is a Gaussian thing?
Why I expect? Well, probably it will be clear from what will be happening later. Yeah. So actually, yeah. So because we can compute something and see that it is Gaussian, but yeah. I think that
it's not obvious that it's a Gaussian.
No, I don't think so. I think that honestly, I think that probably this can be also derived heuristically from like limit shape story. If you think of limit shape, and so probably it should be Gaussian for the same reason. But for me, it is, first of all, it's Gaussian because you can still relate it with Dirac operator. You can still do something like this, like in the simply connected case, but in more general fashion. So here is the main setup that we want to understand. So we have a multiply connected Riemann surface, right? So non-trivial Riemann surface. We probably have a sequence of graphs which approximate it in a certain sense. We look at the sequence of height fluctuations on it, and we want to prove that it converges to the compactified free field. Okay.
I'm sorry.
Yes.
So what's U in this notation?
So as I said, the monodromies of height fluctuations are not integer, but they're integer shifted by something deterministic. So this U is this shift. So we subtract expectation, so we subtract some real, if you think of psi as a vector of monodromies, then this psi dd0, it's an integer vector, and the expectation of integer vector not necessarily integer, so you subtract some real vector.
But so U itself is an element of, is the function on the Riemann surface?
It's a differential.
It's just differential.
Differential, yeah. It's a harmonic differential.
Just fixed throughout.
Yeah. So it should be something which we also have to compute somehow.
You probably arranged by some symmetry that U be 0, right?
No. Not necessarily. So we will see. No, it's not necessarily like that. Yeah. So for example, if you take hexagon lattice on a torus, then it won't necessarily be like that. Yeah. Okay. Basha, did I answer your question out? Yes. Okay. It's very good. Other questions? Okay. Good. So now, I think it's this story was already. Sorry, I'm drunk. It's doesn't work anymore for some reason. Sorry, something happened. Okay. Sorry. Okay, so this is a story that has been studied for a long time. So there are several works, and I think that the case of a torus is quite understood by Cédric Boutier, Berestycki, and Dubida. And there is also a very general result of Nathaniel Berestycki, Ray, and Benoit Laslier about general Riemann surface and Temperley graphs on them. So let me now talk about their result. Let me now describe what is happening there, what's known and what is not. So to begin with, I would like to define what I mean by temporary graphs. I'm not sure if it's a canonical way to denote this type of graphs, but okay, I call them temporary. So we start with some primal graph gamma. And then we look at the dual graph gamma and draw them on the same surface and take what I think is called the medial graph. So we draw them and we construct the bipartite graph whose black vertices are vertices of either gamma or gamma cross, or the dual graph, and white vertices lives in the middle of edges. Okay, so this is a bipartite graph. And it's actually not hard to see that on internal Riemann surface, any such graph won't be dimerable. There will be no dimer covers of it. Why? Because the number of white vertices is actually bigger than the number of black vertices. It's just Euler formula. So we need to modify it somehow. And to make it dimerable, what we do is we remove a certain amount of white vertices. Okay? And now we get our punctured graph, which is now dimerable. Okay, so we look at, we consider such a graph. And what's nice about it is that the temporary bijection, which is, I think you all know this in the simply connected case, still can be generalized to this case. But in this case, in the case of non-trivial surface, one has to consider not spanning forest, not forest consisting of trees, but forest consisting of cycle-rooted cycle-rooted trees, which means that cycle-rooted tree is a subgraph such that the number of edges of it is not equal to the number of vertices. So basically, it's a tree with one cycle. Okay, so yeah, but with these changes, it's still possible to find a bijection between dimer covers of the bipartite graph G and this cycle-rooted spanning forest of certain type, not all of them, but of certain type, somehow related with these punctures on the primal graph gamma. And what is nice about it is that, there is a very nice way to generate random trees. It's actually Wilson algorithm, right? So, and the height function is very well related with certain invariants of these trees. So if you want to consider the height increment between 2 points, we need to actually look at the branch of the tree between these 2 points and compute its winding. It will give the height increment. So this helps to study the dimer model using some soft analytic arguments, soft probabilistic arguments coming from random walk. So, so here's the theorem that due to Nathaniel, Benoit, and Gorab. So let us look at it one by one, so line by line. So they assume that we have a sequence of temporary graphs on our sigma with some mesh, some scale delta somehow encoded there. And they assume that they approximate the conformal structure of this sigma in the following sense. So first of all, the random walk of the primal graph gamma should converge to the Brownian motion and should satisfy uniform cross-seam estimates up to scale delta, up to any scale. So this is the way how the conformal structure of sigma is approximated by these graphs. And they also assume that these removed white vertices converge to certain marked points on our surface. And then using soft probabilistic techniques, they are able to prove that in this case, our height fluctuations converge and have a certain limit which doesn't depend on the sequence of graphs, but it does depend only on the conformal structure of the marked surface. So it depends on the conformal structure on sigma and on how these marked points are situated on it. Okay. But the problem, what remains after this work is to identify this limit with the compactified free field. And the problem of identifying is probably because the Nathaniel, Benoit, and Gorap are using only soft arguments, and it's very nice because they get a very general result, but it's not enough to get to write some precise formulas probably. So that's why this identification becomes a non-trivial thing in this approach. So yeah, it's okay. So actually non-trivial thing in other approach too, but at least now we come to my results. What we want to do now is to change the approach, so since the limit, we know that the limit does not depend on the sequence of graphs. The idea is that to find a certain setup in which these temporary graphs will be nice enough to apply a discrete complex analysis technique, to apply certain hard analysis, and to get certain invariants that would allow us to identify the limit with the compactified free field. Okay. So, any questions? Okay, very good. So, how are we going to do it? There are several standard setups in which like discrete complex analysis technique or harmonic analysis technique is available. Like isoidal graphs, I think that the most well-known setup, or probably t-embedding, the recent development of t-embedding also. But in all these cases, we kind of need, we kind of use the Euclidean structure of the plane. So we need to, our graph must satisfy certain geometric conditions formulated in terms of Euclidean structure of the plane. So we want to have something like this on the surface. Preferably, we would like to have a flat metric on our surface. But of course, if Euler characteristic is non-zero, then there will be no flat metric. But what we have is we have this marked points sitting on our surface, and we can make use of it. So first of all, let us assume that the boundary is empty, just to make things simpler. Everything works with non-empty boundary too, but I don't want to talk about it. And now what we can do is we can take our surface with marked points and consider locally flat metric with conical singularities at these points. And for some reason, I would like these conical singularities to have angles 4 pi at each of it. And well, magic happens. The amount of marked points is necessary and sufficient to get this metric, to construct this metric on the surface. So I just wanted to draw some example, so to explain a little bit better what it is. So here's an example of such a surface of genus 2. So what we do is we take this polygon and identify this side with this side, this blue blue side, and this blue side, etc. Just identify by rotating and translating them. In this case, we get in this way we get a surface of genus 2, and we get in the Euclidean metric that you can see on the slide. It induces the metric. It induces the metric on a surface which is regular everywhere except at vertices, and at vertices you will see these conical singularities which I mentioned, 2 of them in this case. Right? So this is an example of such a surface, and actually any such surface can be constructed in this way, more or less. For any such surface, you can see that you have a polygon which you glue together to get a surface, and then there will be some conical singularities at vertices. Okay, so an important thing about such a metric is that this metric might have a non-trivial holonomy. So what do I mean by this? It's again can be seen on the slide. So so for example, let us consider a non-trivial loop that goes like from that blue side to that blue side, and let us look at any vector and see how it transforms when we make a parallel transport of it along this curve. So you see that in the end we end up with this vector to be rotated by some complex number. So this means yeah, this metric has non-trivial halonomy along this loop. And it is represented by multiplication by this exponent. So in general, we can find harmonic one differential such that if we take a parallel transport along any loop, then the vector is multiplied by the exponent of the integral of this differential. Okay, so we call it halonomy one form, and will be important for the future. Like it will somehow be related with the limit that we get. Okay, so now what is the setup that we want to consider? Since we've chosen this conical singularity to have angles 4 pi, we actually can view our surface near these conical singularities as double cover of the Euclidean plane. So then we ask our graphs to have the following structure. So first of all, outside conical singularities, we ask them to be nice t-embeddings. If you don't know what is t-embedding, I will give you an example in a minute, so don't worry. You don't have to think about it. And near conical singularities, we need to have some additional regularity. So we ask these graphs to be isoradial and to be pullbacks actually of isoradial graphs from this double cover. Okay. Okay, so this is the setup, and I want to give you some example of such a surface. That's probably so you don't need to think about t-embedding, about general case. So an example of such a surface is what they call pillow surface sometimes, so square tile surface probably. So how one can construct it? You take a Riemann surface, and you consider a graph on this surface which has faces of degree 4. Then imagine that you identify each of these face with a square on the Euclidean plane of length 1. Then if you glue the squares together according to this combinatorics, you get a Riemann surface with a flat metric, which is regular everywhere except of vertices which have degree different from 4. Right, so at any degree 4 vertex, the sum of angles of these squares is 2 pi, and it's a regular vertex. But there will be some other vertices necessary where we have different sum of angles, different degree, and there will be conical singularities there. So then, for example, if you take the dual graph to this square tiling, then on this surface, then the theorems that I'm going to present to you will be working for it. So you can take it as a working example, although it's not very general example because these surfaces will always have trivial halonomy, right? So we'll have to do something else if you want to take into account all the surfaces. Anyway, so now we can formulate our theorem, but maybe you have some questions up to this point, no?
What's the genus of this picture?
I think 2.
How many conical points should I look for?
I think 2 points. Okay, they're hidden.
They're hidden just behind.
They're behind. Sorry.
Interesting choice.
Yeah.
If you're just considering non-conformal structures, it suffices to just take these translation surfaces. You don't need non-trivial holonomics.
Yes, but if I want to place conical singularities at random points, then I would have to have non-trivial holonomy. So the idea is that if my surface has trivial holonomy, then I can define this global north direction. It will get me one form, holomorphic one form, dz, and it will have zeros at these conical point singularities. So this is a huge constraint that conical singularities are zeros of some holomorphic one form. Yeah. So if I want to, So if I want to work with general case, I need to cook up something else. And I will probably tell you how I do it a little bit later. Yeah. Okay, so this is actually the point where I need to use t-embeddings.
Can I just check? I mean, I thought I understood that you want in the neighborhood of your puncture that the graph coincides with the pullback of an isoradial graph?
Yes.
And this is the case on the graph that we're seeing here?
Yes, of course, because it's at this point it will be pullback of square lattice.
Really?
Yeah.
Okay.
Yeah.
Okay.
Yeah.
Even globally, not just.
I mean, what I can do is I can fix such a graph, and then I can refine it more and more and more, and then like each conical singularity will have like small neighborhood where it's a pullback. So they're like on macroscopic distance. Okay. Yeah. Yeah, actually, if I didn't care about positions of conical singularities, I could have approximated any surface with this translation surface, of course. But yeah. Okay, so now the theorem, the main theorem. So it has 3 statements. So first of all, so based on the work of Nathaniel, Benoit, and Gorab, we can assume that height field is tight, half fluctuations are tight. So then, if they are tight, then any subsequential limit is given by a certain compactified tree field. Yes, for some deterministic shift U, which we have this subscript U, it actually tells us that the monodromy vector would be integer up to some deterministic shift, which actually depends on the sequence of graphs. But if the sequence was chosen to be Temperley, then this, and furthermore, removed white vertices converge to these marked points, then this shift which we have in the limit is the Halonoby-1 form. So it's related with the metric, with this specially chosen metric. And finally, since we don't consider only temporary graphs, I want to state this too, that, if the surface was chosen generic, so basically I need some theta constants to be non-zero, then actually I can prove that this height fluctuations the sequence of height fluctuations is tight. Yeah. Okay, so I want to emphasize a certain thing. It seems like in the case of Temperley graphs, the limit depends on the metric. Actually, it doesn't depend. It can't depend on the metric. It should be conformally invariant. But the thing is that we chose a metric in a special way. We chose it in accordance with these marked points. It actually depends on how we removed white vertices. Although we deformed the graph only locally, well, it affects the answer. This should be taken into account. Okay, so this is the theorem. And I have to mention that it's still not enough to conclude that limit from the work of Nathaniel, Benoit, Gorab is the compactified tree field, because they have certain assumptions with respect to smooth metric, and I have singular metrics here, so we need to generalize the result a little bit. I think it's totally within reach, so it's work in progress, but still, yeah, at this point, there is still some work to do. We should remember it. Okay, good. So let us now speak a little bit about how this theorem is proven. It will be a little bit technical, but I hope that maybe you'll learn something from here. I think it's beautiful. Anyway, so
sorry, can you go back to the theorem again? So you're saying subsequential limits?
Yes, here, I mean, yeah.
Okay, so there is.
Yeah, so if you don't impose anything on your graphs, if they're not temporary or whatever, then there might be several limits. Basically, the only difference will be that this shift is somehow depends on the graph. So for example, if you take the hexagonal lattice on a torus, which is not like, it's just like this, right? So not rectangular one, then the limit would somehow depend on something modulo 3. Yeah.
So there's like 3 possible limits.
Just 3 possible limits, yeah. Yeah, in general, it will somehow depend on the graph. Okay.
And it depends on the fine. I mean, like, but that's not the part that depends on the fine details of how which white vertices you remove, or.
It depends on some certain global things. It depends on, yeah. I think I don't want to go into too much details, but yeah, somehow maybe I will. I will comment on it a little bit later during the so I will try to memorize it that I need to do it. Okay, so now how the proof goes? Just a little bit of technical details. So okay, so remember we have our sequence of nice graphs approximating our surface. Yeah, and what I claim is that there is a natural choice of Castellan weights associated with these graphs. So we assume that these graphs were t-embedding, right? So the dual graph is t-embedded in our surface. So there is a way to produce Castellan weights associated with any t-embedding. The thing is that on a surface, well, if you know how these t-embedding Castellan weights are constructed, well, they depend actually on how you embed the graph into the the graph into the plane. And here we don't have any global coordinate. So if you just follow that rule, then we get something multivalued. We don't have actually defined weights. So we have to correct them somehow to cancel this monodromy. This will be some kind of gauge that we use. And we can choose it in many different ways, actually. And this is it's natural because not all Castellanian weights are gauge equivalent if you have a non-trivial topology, right? So but what I claim is there is some natural choice to cancel this monodromy that appears, to choose this gauge. Right, and then, well, probably I should have had this before. So then this Castellanian operator will well, we know that Castellanian operator can be treated as a Dirac operator. There is a strong evidence that it is a Dirac operator. So in this case, it will also be true, but it will be Dirac operator perturbed somehow, perturbed by certain 0-1 form. That depends on the graph. And here is how this answer subspacial limit actually determines, because this form, it might be different for different graphs. So yeah, it's this is an analytic way to find out what should be in the limit. So yeah, you construct this 0-1 form purely from pure combinatorial information. You require that something is real, and then you get this homology class, and it is something that appears in the limit. So yes, there is a precise, there is a concrete procedure of how to determine it. Yeah, and then what we want to do is we want to take this Dirac operator and perturb it even more. So we introduce perturbation of this form. And I think that such things first appeared in Dubida's work, so it should be credited to him. Okay, so morally, we can think that we introduce some gauge, some other non-trivial gauge, but it's not actually like that, because alpha is an arbitrary 0-1 form. It doesn't have to be close to something, so it's just a smooth 0-1 form. So yeah, and here the integral depends on the path, and we integrate along an edge specifically. Okay, so but then what I claim is that for any alpha, the determinant of this operator still has a meaning that we can actually utilize for our purposes. So there is this messy formula that I want to explain you. So first of all, I claim that if we take the determinant and normalize it somehow, I will explain it a little bit later. Then, well, we know that in general on a Riemann surface, if you take a determinant of Castellanian operator, it doesn't give us a partition function, but give us a sign partition function. There will be some signs somehow determined from some quadratic function, some spin structure, if you wish. So, well, it appears here. So Q is certain quadratic function on the vector of monodromies. Okay, and and the second summand that which expectation we compute is actually this expression which relates the whole story with the height function. So we have the height function here, and we differentiate it. We take the wedge product with the imaginary part of this form alpha, and we integrate. So in a sense, what we get here is characteristic function of this random variable, in some sense. If you think of this as a function of alpha, that this is some sort of a characteristic function of our random variable with respect to some signed measure. And well, we can believe that if we control this expression, then probably we can deconstruct the distribution in the limit. Right. So and there is this normalizing factor, which is a little bit mysterious, but we will see how it plays its role later. Okay, so this is the formula. I keep it on the slide. This is the same formula. Now we do the following thing. So first of all, we look at the corresponding continuous operator, and we look at this expansion near the diagonal. So near the diagonal is just a Cauchy kernel plus some second term, right? And right, so then what we want to do is we want to control this this quantity, right? So to this end, we compute this variation, because this variation will give us will be easier to compute to control the quantity itself. So then we get this simple algebraic identity. And when we expand everything, then we see that that give us a certain sum where we have this inverting kernel, and we subtract, we kind of subtract this full plane Cauchy kernel from it. So we regularize it. In the end, we, in a certain sense, we integrate this second term over our surface. So indeed, this is indeed the case. So what we get in the limit is certain, is approximately certain, a certain analytic formula that relates this whole story, this variation with the Cauchy kernel in the limit. And what I claim is that it resembles some computations which was made by Quillen, I think, a long time ago. There is this paper of Quillen where he defined determinant of family of Cauchy-Riemann operators, and along the way he needs to compute some curvature, so he studies the variation identities of zeta regularized determinant of the Laplacian associated with this Cauchy-Riemann operator, and he arrives at more or less the same identity. So in the end, we see that this Cauchy-Riemann operator is determined, which is normalized by this factor. It somehow, we should think that it converges to the determinant of the corresponding Dirac operator, in a sense. Yeah. So so this is the main technical thing, and of course I omitted a lot of technical work here because we need to estimate the inverse operator, and we need to find it's asymptotic along the diagonals, pretty non-trivial task, but it's technical, so it's not very interesting to speak about. Yes?
Yeah, so it seems like somehow, like the fact that K inverse, you can write it in terms of the flat metric. I mean, because it's kind of surprising that you get the same formula for like for B minus W. Is that somehow like part of this proof is that the inverse Castellane matrix on these like conical surfaces has to do with the flat metric?
Yeah, sure. Yeah. It's not very surprising. Yeah, if you expect that it converges to the Dirac operator, then yeah, of course. I mean, that somehow approximates Dirac operator. Why not? Yeah. Yes.
You're not near one of the singular points.
So what's happening near singular point, right? Well, not this. Then you can, I mean, no, it's actually, no, this is what happened in singular points. The thing is that, this expression depends on the coordinate. If you choose a coordinate, like smooth coordinate, then you still have this expression. But the analysis is complicated because we kind of have these distinguished coordinates, which are not very nice at this cone. But otherwise, I mean, we expect more or less the same things is happening, but it's just, like written in different coordinates. So, I mean, on the discrete level, it's complicated, but you can actually, since in this case, I cheated a little bit because I asked my graph to be double cover of some planar graph, and then I can work with multivalued functions on that planar graph. So it helps. Okay. So other questions? Okay. So. I wanted to say a couple of words of how you reconstruct the instanton component from here. I'll probably tell it very briefly. So now we can control these expectations. And, we remember that we assume that we expect that our vector of monodromies converge to that discrete Gaussian vector. So what we do is we look at the same expectation for this discrete Gaussian vector, and using some clever Poisson transformation technique, we can actually express this expectation in terms of theta functions, and this gives the answer, basically. So then, using this relation, we can prove that, and this variation identity, we can prove that this expectation converges to what we want, and we can somehow derive, reconstruct the distribution from this fact. Okay. So so there are many technical details hidden, but ideologically it's pretty simple. Once you know what to compute. Okay, so for during the last 5 minutes, I guess, do I have 5 minutes? Okay, good. So I want to tell you a little bit more about combinatorics of the story, how we link it with temporary graphs. Okay, so there will be no analysis now, so don't worry. Okay, so remember the setup. We had our Riemann surface. we choose a locally flat metric with conical singularities at marked points, and we choose our graph to be t-embedding in the bulk, and we want it to be also double cover of an isiradial graph at conical singularities. So first, why double cover of an isiradial graph? How is it related with Temperley setup, right? So why we want to say that these conical singularities are actually white vertices that are removed? So there is a pretty simple combinatorial observation that if we take a double cover, for example, of a square grid, so let's think about square grid. The square grid is a Temperley graph. It's a medial graph of a graph of its dual, right? Of two lattices, basically. So then the double cover will not be a medial graph anymore, right? So this right face of the primal graph contains two crosses, two vertices of the dual graph. But you can look at it a little bit more, a little bit closer, then you see that actually its medial graph is one white vertex removed. So yeah, so conical singularity of this type of cone angle 4 pi indeed correspond very well to removing white vertices. So this is first combinatorial observation, which explains why I chose these conical singularities, because I think that the story can work actually for any other type of conical singularities too. So another thing is how we construct this t-embedding on a general Riemann surface, which has non-trivial holonomy. It's another story. So there is the following construction that I just want to demonstrate. So we start from some arbitrary collection of points in our sigma, which will be vertices of our primal graph. It must be not very nasty collection of points, okay? So it must be kind of equally distributed, but there are no geometric constraints. We only probably impose some geometric constraints near conical singularities to get nice pattern near that. But in the bulk, we don't, just arbitrary thing. We take the Delaunay triangulation of it, right? And we draw the corresponding Voronoi diagram. So, yeah, and we want to take the medial graph of this thing. And the problem is that, if this Delaunay triangulation was arbitrary, then they might probably not drawn very well with respect to each other. So dual edges do not intersect each other at all places. But what I claim is that if we did it in this way, if we took the Delaunay triangulation for a diagram, then the dual graph can always be embedded very nicely. And we get a very nice t-embedding, which we can work with. It's like technique from the paper of Chelkak, Russkikh, and Laslier is enough to do the whole complex analysis that we need in this case. Right, so this is it. Thank you very much.